All right, so what I'm looking for, or let me reiterate this since I wasn't recording. The cheat sheet will be due, and we'll talk about it in just a moment, will be due Tuesday at midnight. Stack as template is Thursday at midnight. The project itself will be early next week. I currently have it next week, Tuesday at midnight. I think that'll be enough time. We'll play it by ear. Regarding the content of the exception cheat sheet, oops, I didn't want to edit. I just wanted to click on it. Oh, I guess I was just clicking on it. So the tech pros here, which isn't very illuminating. Submit your 1 page or less cheat sheet document on the exception handling facilities of C++. Try, throw, catch. Meaning that if I was to ask you to go into my 111 class and teach exception handling, you would run off and figure out what try is, what throw is, what catch is, and maybe a little bit about what this whole standard exception header file is about. Okay, and so that's all I'm looking for is find out what those things are, explain each in a sentence or 5, doesn't matter, whatever it takes. And what makes it easiest is to put some examples in there. This is what try looks like. This is where you would throw. This is a catch. This is a default catch clause. And really, low stakes. I guarantee you, I'm not looking very long at these things. I just need to drive you to the material to learn how they work. They really aren't that complex, and it's a waste of your time for me to lecture on them. Yes.
And do you want like the inheritance hierarchy for the?
I don't need that. But if you've already done it, I mean, what you have there is fine. Turn that in and you're set. All right, so let me back out of this and let me talk about this original stack.cpp. Oh, looks like I've already got it there. So let me all right. So what you're going to do is you're going to take over here. You're going to take this class, this stack class. This is something that was pulled off the internet. And there are going to be 2 things you're going to do. You're going to convert it to a template. And we can talk a little bit about that. We can talk a little bit about it at the end of the period if there's time. I suspect there may not be time. Otherwise, I'll talk a little bit about it next time, about how to convert it to a template. And once it's a template, then you need to implement exception handling on it. Now, it isn't as easy as it sounds. In fact, I can guarantee anyone in this class who does like that first thing to understand try, throw, catch, if you think you understand exception handling and then try and implement exceptions properly in this class, you'll do it wrong. Because what I'm asking for is not quite what you think I'm asking for. That discussion will come a little bit later in the week. For now, what I want you to do is to understand what this class does. So I'll bring up my sketch pad and we'll draw some pictures and walk through some of this code. Okay. So what I'm going to do is I'm going to create a file called useStack. Bring in this. I'll pound include. So here's a huge no-no. I say this many, many times. Never, ever, ever pound include a CPP file. The only reason I'm doing it now is because templates, like the standard template library, what do you need to do in order to use a vector in the standard template library? Pound included, right? Okay. After you do the exception handling how-to, the next thing is to convert the code on the right to a template. Once you convert it to a template, it all sits in a header file, and you pound include it. So I'm just kind of winking at the fact that this is a CPP saying, in 48 hours, you're going to convert this to a template, and you'll be pound including it. So that's why I'm doing it. All right, and you'll rename it. You'll call it originstack.h, or just stack.h. Why not? Because a lot of the time you can make it work if you pound include a CPP, but it's very, very brittle and you'll end up breaking it. The typical use case, well, let me back up. So the compiler is designed to compile separately each source file, so I would end up with a useStack.o and origstack.o, and then the linker would link the two object files together. If I pound include, then that all becomes one compilation unit, and I only have one .o file that's a little bit gratuitous. The linker works on it, puts the bootstrap on it, and then we have an executable. A lot of times the reason, if you don't understand how do I want to say this? If in main I want to create a stack, and all I have is this, that won't compile because the compiler has not seen stack. The proper way to solve that problem is to take the declaration of the stack class on lines 1 through 16 and put that in a header file. I pound include that. That serves as information for the compiler so that it will compile line 7 correctly. The other way around it is you leave origstack.cpp the way it is and you just pound include it, because that does then get you the declaration here. The problem is now you expand your application and you get another source file that uses stack. Well, if you pound include origstack.cpp in there as well, then when you get to the linker, it'll all compile fine, but you'll get to the linker and every one of these member functions you'll get redeclaration errors. So you can make it work in simple examples, but once you use the language development environment as it's intended, you're eventually going to hit a case where everything just falls apart on you. All right. So let's do a little exercising of this. I create a stack. I'm going to say cout size equals my stack dot, is there a size function? Yes, there's a size function, so I'm calling that. And then I'm going to say my stack dot push, and I'm going to push the number 8 on there, and I'm going to print the size of the stack again. So let me come out of here. I will compile my useStack.cpp, and I suppose I should do that. Okay, nothing unexpected there. So let's now look in detail at what's occurring. My default constructor here on lines, getting my screen repaired is in the works, so I should have a new screen sometime within the next couple of weeks. Lines 20 through 25 is the code that gets run when we create that stack. And as we know from the whole polymorphism exercise, an object, a class object that you create, in this case, what did I call it, my stack, is nothing but the data, right? It's nothing but the data, and we know that when this thing gets compiled down, all the member functions get compiled as, quote, normal C-style functions. And when I'm invoking a member function, all I'm doing is passing that data structure into that function to run as this parameter. Okay. So it's entirely accurate then to look at the stack that I created as just a data structure. So let me come back here, and we've got chunk size. Okay, so let me stop here, immediately here. What's the significance of static? Yes?
It's a variable which is shared by all members of the class, but doesn't belong to any one object. It's shared by all objects of the class, but doesn't no separate copies for each.
Right. So yes, I think that's a close enough definition. There's only a single instance of this variable called chunk size. There will only be one of them if there's one stack object you create, 100 stack objects you create, or 0 stack objects you create. If you never create a stack object, that variable will exist. Its closest kin, I guess, would be a global variable. Global variables are there are always exceptions, but global variables are generally frowned upon because you could inadvertently modify a global variable in one function, creating undesirable side effects in some other function, right? And the larger the application, multiple developers, that becomes a real-world nightmare. So this is getting us around that. We have the advantage of global variables. It has the scope of a global variable. It comes into existence the moment your application starts, and it goes out of existence when your application dies. But the visibility is different. And it is private, so it's only visible to, only accessible, and I won't say modifiable, because note that it's constant. So when it comes into creation, it's set, and it won't be able to be changed. But at least the code, the member functions for the stack class are at least able to look at it. Its chunk size is 10, yes?
Are the static variables which are parts of the class, are these stored together with all the global variables in the .data section?
I couldn't tell you where they're sitting.
But they're not on the.
I would assume that they would sit wherever the other global variables are sitting, because by making this a static variable and making it private, the only thing we're changing is the errors that the compiler will generate. Right now, if and some just in main, I try to access chunk size, it won't compile. So it doesn't change the semantic of global variables. It's just changing how the compiler reacts to our attempts to use it. It sets a very small set of valid use cases for us to be able to use that variable. So that's all just the compiler at compile time limiting our use of it. I want to come back to my drawing now, and I will say chunk size is equal to 10. I'll put that there. Now the other variables that we have that aren't static are the maximum size, current size, and base. Maximum size, current size, and base. Now base is a pointer, so I'm going to put that little asterisk right here just to remind that it's holding an address. I think that's it, just those three. Okay. So the moment I enter a constructor, the very first thing that's done is memory is allocated. The moment I create a class, I'm now using C nomenclature, the moment I create a class object, the first thing that's done is memory is allocated for it. And I'm actually going to need this very thing in a little while, so I'm going to preserve a copy of it that I can get at later. And I need to copy and paste it somewhere. Okay, so that memory is set aside. Now the initialization list can go ahead and do its thing. The current size is going to be set to -1. So that's -1. The maximum size is set to the chunk size, and chunk size is 10. So that's 10. And then for base, there is an allocation of an array of integers. In this case, whatever the chunk size is, which again is 10. So we get, let me go ahead and do that. Oops, I don't want it to be, well, yeah, it can be blue, I guess that's fine. All right, that gives us 10, and with that allocation, our pointer then is pointing at the beginning, the address that's returned to us. So all that happens in the initialization list. A note about you'll find that there are throws in here for exception handling. I can guarantee you that every use of exception handling is incomplete in this code that you're giving. So what you should do, the first thing you do when you take your copy of this code before you convert it to a template, anything that's exception handling, rip out of there. It's all incorrect. Okay? So we can ignore that then, based on what I just said. And that's all there is. There's no other code in there. So just by me saying stack my stack, this is what we end up with in memory. Then what I do is coming here, I go ahead and I call the push function, and I push on 8. Oh, actually, let me go ahead and go through this properly. We just did this line. Now we call the size function right here. So let's look at the size function. Stack :size. All right here. And it just returns current size plus 1. We can look at this. Current size is -1. If you add 1 to that, that's 0. So it's 0 that gets printed. Now we do the push function, which is push on an 8. So let me find push. Here it is. All fits on the screen here. What I'm going to do is I'm going to take all this code right here and I'm going to fold it up, because we only fall into this if statement if the current size is equal to the maximum size minus 1. So maximum size minus 1 is 9. -1 is not equal to 9, so that's false. And it's going to be false for quite a while. So that's why I'm folding it. I just don't want it to be littering what we actually see this function doing most of the time. So the very first thing that push does is it increases the current size by 1. So that becomes 0. Is 0 equal to 9? No, it isn't. So what it does is line 75, which is to take base sub current size. Current size is 0. Base sub 0 is going to be this first element here. It's going to assign it whatever this input parameter was, which, looking on the left pane there, is an 8. So I'll go ahead and I guess I can change the color and put an 8 in there. All right. So 972. Again, we go through real quickly. We add 1 to current size. That becomes 1. That if is false, and then we add it to the first element here. What did I choose? 972, so we get a 9, 7, 2, and then we'll go ahead and do 4 more of those. So that brings it up to 7. It's always, the current size is always 1 less than the number of elements. And that, again, I didn't write this code, so I'm not advocating it, I'm just explaining it. We add one, so let's put a little comment here, 4 more pushes, and then I do my stack.push 3. This becomes an 8. Is 8 less than 9? Or is 8 equal to 9? No. So the 3 goes on there. And now, one more. What's a number I haven't used yet? 6. Push on 6. And again, the very first line adds 1 to current size. So this becomes 9. And now, 9 is equal to 10 minus 1. So now we're going to fall into this if statement. The very first thing it does is it takes the maximum size and it increases it by the chunk size, which is 10. So this turns into 20. The next thing it does is it creates a local variable called new buffer, and it assigns an array of integers equal to maximum size, which we had just increased to 20. So now we've got a local variable called new buffer. So I'll just say new buffer. It's a pointer. And it's going to set aside 20 of them. So that is putting there. The next thing it's going to do is there's some exception handling. Don't do that. Delete lines 68 and 69. Line 70 is going to do a for loop from 0 to less than 9. So 9 iterations, 0 through 8. It's going to do what we have here, and what it's going to do is it's going to assign to new buffer sub x whatever is in base sub x. So that's essentially going to then copy all these down. So we have 8, 9, 7, 2, 3. Okay. Now we're going to release the memory that had been allocated to base. So now we're going to take this memory here and we're going to release it. I don't know which way to draw that. Okay. And then the final thing is to base, we're going to assign the address that's stored in new buffer. So this is the address that's stored in new buffer. Now base is going to point to that same address. Now we fall out of the if statement and we do this line that we've been doing on every iteration here on line 75, which is to assign to new base sub current size. Current size is 9, so we're assigning to that whatever element is. Recall that element is our input parameter, and looking at line 17, we see that that's a 6. So it's a 6 then that gets assigned here, and now we're done with push. Okay, so that's how push works. Let's look at this starting on line 45 here, this assignment operator. So the assignment operator is going to be called, if I do something like stack another, and I say another equals my stack. Okay, that's calling the assignment operator on line 45. Just so, I think we did that in this class, another dot operator equals, this is an equivalent invocation of that function. Atypical, but certainly permissible. Yes?
So you could run that assignment as that function call, and it would still work.
That's correct. What I have commented out will compile. So the first thing we have to handle is line 19. And line 19 creates, using the default constructor, a variable called another. So this is where I'd want to copy this. So this gets brought in. Let me go ahead and label both of these. This one's called my stack. This one is called another. And we have the same code running for the default constructor there. Let me just go to it really quickly. It's right here, lines 20 through 25. And there was no code in the body of the function. It all happens in the initialization list. Current size gets set to -1. Maximum size gets set to chunk size. And then there's this 10 integers that are allocated using new. I'll use the same color here. Right. That runs the default constructor. And now we go to the next line of the actual assignment operator, line 20. Pop over here to our stack code. So lines 45 through 59. The very first thing, so the invoking objects on the left-hand side and the right-hand side of the assignment is the argument. So looking back on the code usage here on the left pane, my stack is S on line 45 in the right pane, right? That's S. And note that it is a reference, so it actually is S. It's not a copy of S. S is just another name for my stack. Also note that it's being passed in as a constant, so we do not intend to modify S inside this function. If we did try, it wouldn't compile. The invoking function, this pointer, if you will, is another. All right, so the first thing we do is we delete base. You don't see it there, but once again, just to drive it home, this is implied. Okay. So First thing that happens, I'll use the red, is this memory is released. The second thing that happens is another's maximum size is set to whatever S's maximum size is. So S's maximum size is 20. That gets replaced with 20. Do the same thing with, we do the same thing further down, I guess. All right, so the next thing we do is we allocate maximum size integers and assign it to base. So maximum size integers is now 20, and we're going to allocate 20. Right. And that is being assigned to base, so I draw my arrow here. There. Seems like my pen changed. I can't quite see that. Look here. That should be, I think this ballpoint pen is what I use, yeah. All right. So that was 49. The throw stuff is bogus. 52, we assign S's current size. Which is 9. So that -1 is replaced with 9. And is current size greater than -1? Yes, it's 9. So now we're going to do a for loop. And each of these, 8, I'm not quite sure how to do this, 8 goes in here. The for loop's going to copy 9 in here, and I won't draw any more arrows, but you get the idea. So we get 8, 9, 7, 2, bunch of dots, 3, 6. And then that's it. Returns this. Why are we returning this, by the way? We're not returning this, we're returning star this, which means that another itself is what remains after that function call. Yes?
Are we returning the object itself?
We are returning the object itself, yes.
That, I know that with primitive data types you can do assignment operators in, so you can assign one to another one and so on.
So looking at this expression, this is a valid expression in the language. If I go to the web and I type operator overloading, not operator overloading, precedence, grab this, see what that one looks like. And we find that assignment operator, which is pretty low precedence, but the key for assignment in all of these is that it's evaluated right to left. So that means the first thing that happens is it assigns 3.14 to D. The result of that expression is D. So then D is assigned to C. C now has 3.14. The result of that expression is C, because whatever's on the left is what gets returned, if you will. C is assigned to B, what's left is B. B is assigned to A, what's left is A. There's nothing more to do. We move on to the next line of code. So that implies, well, if A is a number, then that implies that's legal, right? If that, in my case, is a float. It is legal. In fact, you can do that. That'll compile, right? It's nonsensical. I wouldn't advise it. It isn't doing anything useful, but it's perfectly legal. For the same reason that this thing evaluates from right to left and you end up with just a number. So that ends up being the assignment operator. Where's my drawing? That does that. The very last one worth looking at is the copy constructor, which is right here. Oops. Do that, zoom in on it. So the copy constructor is going to create a new one. I think I'll just grab this one right here. We'll bring it a little more front and center. I guess I should look at a use case for that. So one, we saw that from our previous discussions that the copy constructor is called if you pass something in by value. So if I create a function and I have a stack C, when I call func and I don't know, I pass in another, then C is a copy of another, and that invokes a copy constructor, right? So that's certainly one case where the copy constructor would be used. That is going to create C here. And the copy constructor, let me zoom in on it so it's a little bit easier on the eyes. The initialization list is going to set the maximum size to S's maximum size. What I did is I passed another into the function, so another is the copy, is S. S's maximum size is 20, so this becomes 20. We allocate S's maximum size for the number of integers, which is, again, 20. I'm just going to do this. There's 20 of them. We ignore the throw stuff. We ask, is the current size greater than -1? It is. The current size is, S's current size is 9. So we're going to go ahead and do a for loop, and if you follow the logic of for loop, it's going to, I guess I'll use this screen. I don't know how visible it'll be. It'll copy that into there, that into there, and so on. That would have been assigned there. Yes?
I remember on the previous time you referred to this as a deep copy, correct?
Yes, this is a deep copy.
Would it be correct to say that the assignment operator also performs a deep copy?
If the assignment operator is implemented correctly, it does a deep copy. For those curious as to what the shallow copy is, it is if I simply copied the value of this pointer into here, right, which would make this point up to this same chunk of memory. Now I have two separate objects pointing to the same memory, and then if this one dies before this one's then pointing to invalid memory. All right, any questions on that? That's pretty straightforward on how that stack works. That's what you need to have a pretty thorough understanding of what's happening, because you're going to actually have to end up manipulating the code a little bit and clean it up. Still doing roughly the same thing, but it needs to be cleaned up to implement exceptions correctly. Yeah.
About copy constructor, can you pass a second parameter to a copy constructor, like an integer?
No. By definition, a copy constructor contains a constant reference to the same type. You can have more than one argument, certainly, but if you do, then it's not a copy constructor. It'd be a 2-argument or 3-argument constructor.
It's not like accepting a const by reference stack object, and then integer saying the number of items you want to copy.
Yeah, you can write whatever constructors you want, but it's not a copy constructor, because a copy constructor has a very specific definition. All right. Let's finish up by let me ask a question. Tell me about the delete that I've got highlighted there, and I don't have to be that one. It could be this one down here. I'm focused in on the syntax that's typed for that. Yeah.
I think that base is an int pointer. So if you do just delete without the brackets, it deletes that int when at that memory address and leaves the rest of those hanging out.
So base, let me grab that, a copy of that, come up here. There's base. So yes, base is a pointer to an integer. Why is that problematic? If you go to the C language and use malloc, you can allocate an array of 3,000 things. You don't need any fancy thing to release it. Right, and what we're contrasting this with is why that and not that. Why is the language telling us that if we've allocated it as an array, we should delete it as with the little brackets there? Why are they having us add that syntax?
I think it's because int pointer base can either point to a single int or to an array. So you have to explicitly specify whether it's whether to delete.
You're absolutely right that the integer pointer may be pointing to a single int or an array of a bunch of ints. But that was the case in C as well. And there's no equivalent construct in C to have a special release for arrays. Yeah.
Well, in the case of malloc, you're allocating the exact amount of, like, for instance, 3,000 ints, for instance. The size of int times 3,000.
Right.
Array. This one we're not allocating that size when we create it first. So maybe because we don't have an exact.
Well, we do. We are in that right here. That's deterministic right here. We know that we're allocating 10, and that's known at compile time. Or actually, let me take that back. It isn't necessarily known at compile time. The optimizer would know it, given that it's a constant integer of global scope. But let me mix it up the question just a little bit. What if I create stack pointer sp equals new? So what I would do is take that original drawing I had, like this my stack here, with this little 10 thingy allocated when we first started out with this discussion. I would take this and I'd copy it 30 times. So what's happening? Let's talk about the allocation. What's happening with the allocation? So first it's assigning whatever our data, the size of our data here, which is going to be that unsigned integer. That'll be the size of an integer. That's the size of an integer. This is going to be the size of a pointer. So those three attributes times 30, it's going to allocate, right? That much space. Then it's going to iterate through that memory that's already been allocated and is in place. It's going to run the constructor on this chunk, and then it's going to run the constructor on this chunk, and it's going to run the constructor on this chunk. It's going to run that constructor 30 times, and when we run that constructor 30 times, we're going to get 30 allocations that look like this, and then 30 bases, each pointing at their respective chunk of dynamic memory that have been allocated, right? Okay. So let me come back down here. When I release this, what does it need to do 30 times? Run the destructor, because what does the destructor do? Let's find the destructor here. It releases those 10 integers or whatever they've grown to different sizes. Now let's not get hung up on this. I don't want to confuse where I'm focusing attention. All we have to know is this is releasing memory that was allocated dynamically. I want to focus on this use of the braces here. So here we get the exact opposite of what happens with the new, which is first the destructor is run 30 times, and then after the destructor is run 30 times, then that huge chunk of memory is released back to the system. And we can see that it's vital that it runs the destructor 30 times. because we have to release this allocated memory 30 times, so we have a massive leak. But here's the next piece of the puzzle. So let me ask a silly question. How many times is the destructor running? 30. Okay. What I'm going to do here, yeah, that's 30. How many times is the destructor going to run?
Times.
But you're the compiler. Is there any way for you to know how many times to run the destructor? There's no way for you to know. So it turns out that when you allocate complex objects like this, I'll borrow this space right here, it will allocate a chunk of memory. But if we were to see how much this was, let's go back to my original of allocating 30 times. We would find that the 30 times ends, say, right here. So this is item 0, 1, and way over here is the 30th item. And then there's actually enough room here to hold a number. When you call new, that number that's returned to you is not this number. It's this number right here. So when I say delete with brackets, then it knows, aha, I actually allocated memory here. I have to back up, get that number, run the destructor this many times, and then when I release the memory back to the system, it's the memory that starts right here that's released back to the system. If I don't put the brackets, then it just blindly releases memory back to the system starting here. And the key thing about releasing the memory starting here is it doesn't work because I didn't allocate memory starting there. So you get a seg fault or something similar. So that's what the braces do, is it tells the compiler that you have this hidden information and you need to incorporate that and run the destructor that many times and then release starting at a different address from that you as the user are using. You as the programmer. Also, that number, how it's stored is implementation dependent. So what I've shown is logical, and there are a lot of implementations that do it that way, but that 30 could be anywhere if we don't have any idea. It depends on the compiler implementation. Yes?
So, clarify, when we're allocating a whole big chunk of our block of elements, we're having additional data stored behind the scenes.
Yes.
Tells us this happens.
That's correct. Additional data is stored as part of the allocation, yep. Yep. Okay, so I kept you longer than I should have. That's all I have. So go ahead and bust out that how-to, and we'll meet again on Wednesday.